the 500 years since Chaucer's mention of the Milky Way, we've discovered that our galaxy is by no means alone in the universe.
About 50 years ago, it became possible to start unlocking the secrets of the stars, how they form and how they change, how they fade. But at about the same time that astronomers were unraveling these mysteries, an entirely new problem was being encountered. In the 1920s, Edwin Hubble was able to show that the Great Spiral Nebula in the constellation of Andromeda was actually a huge galaxy of billions of stars. M31 is similar in size and shape to our own Milky Way galaxy. And today we know that there are billions of galaxies beyond the Milky Way. But our understanding of their nature, their formation, and their evolution really lags decades behind what we know about the stars. In any case, we have that ruggedly handsome, pipe-smoking California astronomer, Edwin Hubble, to thank for getting us started. And he started by classifying galaxies according to their shape.
A galaxy, it's best to show you a picture of galaxy. That will save a few thousand words. This is a photograph taken with the 48-inch Schmidt telescope at Palomar Mountain. This is now the second largest Schmidt telescope in the world, but when this photograph was taken, it was the largest. This is a galaxy. The distance in the sky from one end to the other, on this plate, it's about 6 inches, roughly. But in the sky, this corresponds to a distance of about 120,000 light years. The reason it looks so small is that this thing is a little over 2 million light years away. At that distance, it looks small. It's so faint that from smoggy Los Angeles, you can't see it. But if you get out away from the smog, you can. It's about a fifth magnitude object, roughly. Contains approximately a trillion stars, slightly larger than our own galaxy. The existence of this spiral galaxy in the constellation Andromeda is where you're looking. The existence of this object has been a great deal of help to us in understanding our own galaxy. We're inside our own galaxy, and it's difficult for us to get a global picture of it. The same way it would be hard for us to know what we ourselves look like if we couldn't see other people. Well, it'd be hard for us to understand what our own galaxy looks like if we didn't have this one like our... This is the closest galaxy to us that's like our own.
The great galaxy in Andromeda was first proved to be a galaxy in the 1920s by Edwin Hubble using the 100-inch reflector at Mount Wilson. Hubble and his associates continued to define hundreds of other so-called nebulae as galaxies, great islands of billions of stars. Hubble's first work was the development of a classification system for the galaxies according to their shape. The galaxies fell into two broad groups, round or elliptical systems and spirals, with some of the galaxies having irregular shapes. The elliptical galaxies were grouped from the spherical, E0, to the most flattened E7. The spiral galaxies were subdivided into those that had bars, or SB galaxies, and those without the bar, S galaxies. These groups were then graded from A to C, according to the size of the nucleus and the tightness of their spiral arms. Hubble's complete classification system was referred to as a tuning fork scheme. Hubble published his system with a photographic atlas of some 900 galaxies in 1926. The modern revision of Hubble's system includes a group of armless disk galaxies, both with a bar, SB0 galaxies, and without, S0 galaxies, and two groups of irregular galaxies.
Classifying galaxies according to their detailed appearance is an important first step in coming to grips with them. But in order to understand why there are these various shapes of galaxies in the first place, we have to learn some of the same basic information that we try to obtain for the stars. The masses, the sizes, how many there are of the various sorts of galaxies. And to get that information, well, we have to know the galaxy's distances. But we can do that by applying the technique of the standard candle again, something that tells us how bright the galaxy truly is. Well, by knowing that and comparing it with how bright it appears to be, and by knowing how light diminishes with distance, we then can learn the galaxy's distance. But first, we need that standard candle.
The sun is not a very good standard candle for two reasons. One, it's too faint. Though it seems very bright to us because it's quite close, as stars go, it's a relatively faint star. The other reason it is not a good standard candle is that stars such as the sun don't call attention to themselves. They don't wave flags at us. If I take a picture, for example, of another galaxy that is composed of some 100 billion stars, how do I know which of those stars is a one solar mass star? So what I need is a class of stars that are brighter than the sun and which in some way call attention to themselves. Well, there are two kinds of variable stars that are very satisfactory for these purposes. A natural question that arises at this point is how far away can a galaxy be and still allow us to find R. Lyrae and Cepheid stars in it? With our telescopes, such as the 4-meter telescope here at Kitt Peak or the 5-meter telescope at Palomar, we can identify stars down to only 21st or 22nd magnitude. So if a galaxy is too far away, we simply will not be able to see the R. Lyrae stars or the Cepheids. The R. Lyraes are bright enough to get us out to the Magellanic Clouds, which are a pair of galaxies, which are probably satellites of our own galaxies, at a distance of 50,000 parsecs. So with the R. Lyraes, we can go out somewhat beyond 50,000 parsecs, but not much beyond. So they're quite suitable for getting the distances of a pair of nearby galaxies. With the Cepheid variables, we can reach a distance of some 3 million parsecs, and that will get us the nearest galaxy, which is very much like our own, the Andromeda Galaxy, or Messier 31, and I'll use M31 to denote that. And that will just get us out to the galaxy M81. So with Cepheids, I can determine the distance to M31 and M81, two nearby galaxies. This hardly gets us out of the local swimming hole, so to speak. We have only just begun to sample the universe by getting to these two galaxies. So we need some secondary class of standard candles. And the objects which we will use as secondary standard candles will be novae, globular clusters, and brightest stars. And these three classes of objects can now be calibrated. That by calibrate, I mean we can determine what their intrinsic brightness is by simply measuring their apparent brightness in M31 and M81, because we have used the Cepheids to determine the distance to those two galaxies. Okay, given these three secondary candles, standard candles, the novae, globular clusters, and brightest stars, we can use them to determine distances out to some 20 million parsecs. That is, with the 4-meter and 5-meter telescopes, I can see novae out to a distance of about 20 million parsecs. That distance gets us out to the first large grouping of galaxies, the Virgo cluster. So with these secondary candles that get me to 20 million parsecs, I can determine the distance to the Virgo cluster. Once I go beyond the Virgo cluster, my secondary candles are too faint. I simply can't see them anymore. For example, if I want to go to the Coma cluster, which is approximately 10 times more distant than the Virgo cluster, I will be unable to see them. So then what I need are tertiary standard candles, and the candles that we use there are the brightnesses of galaxies themselves and supernovae. And again, the way in which I determine their intrinsic brightness is now I know the distance to the Virgo cluster. I look at the brightness of galaxies in the Virgo cluster. I look at the brightness, the apparent brightness of supernovae in the Virgo cluster. I know the distance. That tells me their intrinsic brightness. I can then look at galaxies and supernovae beyond the Virgo cluster. And these two together allow us to extend our distance scale out to some 5 billion light years, which means, in terms of a look-back time, means that we are able to determine distances back, nearly halfway back to the origin of the universe.
It's very difficult to appreciate the enormity of a galaxy. One of the ways that has been called to my attention to bring this into focus is to suppose that you had on the wall of your study a picture of the Andromeda Galaxy that, say, covered the entire wall. We'll assume that every man, woman, and child in the United States, say 200 million people, each have a library of 2,000 volumes. One of these libraries is in your den. You pull a book off the shelf, and you start counting the letters, not the words, but the individual letters on the first page of that book. And each time you count a letter, you're entitled to move a thumbtack 1 mile from the edge of the Andromeda Galaxy toward the center. You count every letter in your library. If you're married and have 2 children, why, there are 3 more libraries of 2,000 volumes in your house. So you count all the letters in those, and then you go next door and knock on your neighbor's door, and you count all the letters in his libraries, and you work your way down the street and around the block and through the city and through the 48 contiguous states and Hawaii and Alaska. And then one might ask, was it really necessary to count all those letters in order to get that thumbtack across the Andromeda Galaxy? The answer is the thumbtack at this point would only be halfway across the galaxy. So you'd have to go back and count every letter a second time in order to get the tack all the way across.
Galaxies aren't distributed at random in space by a long shot. They're grouped. And the group of galaxies that contains our own galaxy and the Andromeda Galaxy, this is what we call the local group of galaxies. And the local group of galaxies consists of ours and the Andromeda spiral and at least 24 dwarfs. How many dwarfs there are, we don't know. But so far, we've found about a couple of dozen dwarf members of the local group. So in the local group, there's something like 25 to 2, roughly. But if you add up the mass, of the material within a couple of million light years, you find that something like 90% of the mass, at least, is in our galaxy and in the Andromeda Galaxy. And you add up the contribution of matter of all the dwarf galaxies, you don't get much. So there are a lot of these little things, but they don't add up to much.
If I draw schematically a spiral galaxy, I can draw a central region here, the nuclear bulge of the galaxy, and then I can draw a pair of spiral arms which come winding out like this. There are 2 arms in this galaxy. And then I can make observations of a star, which would be at a point out here, and would be approaching you with a velocity which I can label v. And I can rewrite this equation in the following form, in a very simple form. I can write that the mass of the galaxy will be equal to the square the velocity of the star, which we measure from its Doppler shift, times the radius, where r is the distance of the star from the center of the galaxy, and divide that by the gravitational constant, and that gives me the mass of the galaxy. So it's a simple application of the ideas developed in the 16th and 17th century.
We may be able to estimate a galaxy's size and mass and the number of stars in it, but we still don't know how the galaxies are born and how they evolve and how they die, and why the bewildering variety of shapes, the zoo of galaxies that we see. Is it possible that some are young and some are old? Are the elliptical systems young galaxies which, as they age, become spirals with large, bright central regions, and then spirals with the bare suggestions of arms, spirals with arms partially opened, spirals with arms fully opened, and finally galaxies with irregular shape? Or does irregularity in structure suggest the reverse sequence? Are irregular galaxies the young ones, which, as they age, change to spirals with open arms, and then evolve through the spiral types into tight ellipticals?
Current wisdom has it that the main Hubble types, ellipticals and spirals or disk galaxies, formed in the following way. Each of them started out from a mass of rotating protogalactic material. Depending upon the efficiency of star formation during the galaxy formation epoch, the rotating protogalactic mass became either an elliptical galaxy or a disk galaxy. For those protogalactic clouds in which the efficiency of star formation was great, elliptical galaxies were formed. Very little gas was left over to form a disk subsequent to the formation of the spheroidal aggregate of stars which constitute an elliptical galaxy. On the other hand, for those galaxies destined to become spirals or S0 galaxies, we believe that they started out as lower density concentrations of protogalactic material, concentrations in which it was very difficult to form stars efficiently.
It does seem that ellipticals don't go into spirals, nor do spirals go into ellipticals. But there's a kind of a galaxy called an S0, which looks like a spiral galaxy without arms, a spiral galaxy with no dust and gas. And let me refer to this photographic plate again, if I can, and point out in this cluster in the constellation of Coma here that there are lots of elliptical galaxies in this cluster. And there are a lot of these S0 types, galaxies that seem perhaps once to have been spiral galaxies, but without the dust and gas that goes to make the spiral arms. And it may well be in the jostling or the jolly crockery smashing, as Eddington would have said it, between galaxies here in the core of this cluster, that the dust and gas has been swept out of these former spirals, and that's why we have some of these, it looks like spirals but without arms. Well, we really don't know.
Another very important factor is the rate of initial star formation that went on in these galaxies. And there's a well-known correlation between the current rate of star formation in galaxies and a galaxy's observed Hubble type, in the sense that elliptical and S0 galaxies, at one end of the Hubble sequence, have a very low rate of current star formation, and the later Hubble types, the SBs and SCs, have a relatively high rate of current star formation. This probably hasn't been true throughout their lives. In fact, we know fairly certainly that ellipticals in particular had a much higher rate of star formation early in their history, which consumed all of their gas quite rapidly, whereas SC galaxies, to give the extreme contrast, began their star formation rather slowly and had a lot of gas unconsumed by initial star formation, and are therefore able to continue star formation to the present day.
In order to account for the Hubble sequence in summary, one presupposes that there are two classes of collapse, To account for the Hubble sequence, one imagines that there are two radically different kinds of conditions which obtain during the galaxy formation epoch. One, a condition in which lots of stars are formed right away and not much gas is left to collide with itself, dissipate its energy, and form a disk. Those galaxies in which star formation is very efficient form spheroidal aggregates of stars, which we call elliptical galaxies. Those in which star formation is relatively inefficient and there's lots of gas left over to form a disk after energy dissipation, primarily along the rotation axis, those galaxies form disk systems, spiral galaxies like our Milky Way, and S0 galaxies. The spiral galaxies, those which today have star formation occurring in spiral arms, are those which have some gas remaining to support the formation of new stars. Those galaxies in which all the gas has been consumed or otherwise removed, we call S0 galaxies, disk galaxies which may have at one time formed stars in spiral patterns, but which at the current epoch do not.
These ideas on the formation of spiral and elliptical galaxies do not, however, account for all the variety of shapes that we can observe among the galaxies. In order to account for some of the exceptions and oddities in galactic shape, we are led into the subjects of cannibals and intergalactic collisions.
M31, our famous neighbor, has around it an object very small, M32, which is an elliptical galaxy, which by its color we would think should be a much brighter galaxy. The fact that it isn't brighter than it isn't seen to be brighter than it is interpreted as the fact that it's been stripped as it's come close to M31, and that it is currently spiraling into M31 and losing its mass, i.e. M31, Andromeda, is cannibalizing its neighbor M32.
It's been suggested that galaxies eat each other. That is to say that normally bright galaxies absorb some galaxies that are around them. Let me show you some examples of this so-called cannibalism among galaxies on these plates. For instance, on this photograph here of the Andromeda galaxy, perhaps this dwarf and this dwarf have been shot out from the nucleus of this. Or perhaps they are, because they're moving around in some resisting medium, perhaps they're being sucked in.
When we look at it, this is M31. If you take a photograph, you will see that there's a small round galaxy down here, an elliptical galaxy, and this is M32, Messier 32. For a long time, it has been noted that there are optical peculiarities in M31. It appears as though this galaxy is distorted. Furthermore, it was thought that the velocities of the stars on this side of the galaxy were slightly different than the velocities on this side. And that was taken to be evidence that M32 is gravitationally perturbing the stars in M31. And by that, I mean simply that it was supposed that M32 is close enough to M31 that its gravitational attraction on the stars alters their motion somewhat. More recently, an astronomer at the University of Alabama by the name of Gene Bird has shown that he can explain the peculiarities in the motions of the gas in Andromeda if he assumes that M32 has recently punched through the disk of Andromeda out here on an orbit that would come out of the paper like this and is coming back down in. And if it is presently some 5,000 parsecs in front of Andromeda, going towards it and about to again crash through the plane of Andromeda. If that is true, he has shown that you can explain the peculiarities that you see in the velocities.
The possibility of galactic collision has also been offered as an explanation for a pair of galaxies called the antennae. Two American astronomers, Jury and Alar-Tumre, have used computers to simulate the effect of a particular galactic interaction. This film illustrates the result of the collision of two massive galaxies. Long arms are drawn out by tidal forces and the original angular momentum of the galaxies. This is a pair of galaxies, the antennae on which the simulation was based. Other astronomers have used computer simulation to investigate the formation of a ring galaxy. Here, the smaller galaxy penetrates the disk of the larger one, causing the ring to form. This is the actual ring galaxy. The similarities between the results of computer simulations and the peculiar galaxies actually observed by astronomers have supported the theory of galactic collision.
In the last decade, a great deal of attention has been focused on galaxies, and of course, we've learned a great deal more about them. Well, for instance, we now know that galaxies can collide, or at least closely interact. And when they do, well, we see peculiar shapes, those kinds of odd galaxies that we couldn't explain before. And we also know, unlike the stars, which are forming and dying continuously, that the galaxies were all formed at more or less the same time in the history of the universe, about 10 billion years ago. This means that we don't see galaxies of many different ages, and in fact, to see galaxies that are much younger than most of them, well, we have to look very deep into space. And of course, this means we're also looking very far back into time. Well, galaxies are interesting in themselves. They are the most basic fundamental things that we can look at least on the large scale. Not only are they interesting in themselves, they're also important for us to look at, because galaxies tell us about the size, the shape, the behavior, and the ultimate fate of the universe.